Many of us have been interested at one point or another in gaining an understanding of quantum mechanical phenomena. It's widely agreed that our mathematical tools for predicting the behavior of quantum mechanical systems are powerful, but even those who have a thorough understanding of the use of said mathematical models by virtue of their ability to calculate probabilities don't necessarily have a clear and distinct idea of the actual things which cause the observed phenomena of experimental quantum mechanics. The question many of us want an answer to is what sorts of things actually exist at the scale of quantum mechanical systems that produce the appearance of the wave-particle duality, Heisenberg's uncertainty principle, wave function collapse, quantized spin, and quantum entanglement. In this video, my claim will be that the philosophical worldview of perennialism, at least as I understand it, has a ready answer to this ontological question. First, however, I'll describe the observed phenomena of 7 experiments which demonstrate the basic challenges of providing a satisfactory ontology for quantum theory. In a cathode ray tube, or CRT, the negatively charged electrode, the cathode, as it is supplied energy, seems to transmit a beam of particles to the positively charged anode. If we drill a hole through the anode and place a phosphor-coated screen beyond the anode, we will see an image appear on that screen corresponding to the shape of the hole drilled in the anode. If we minimize the voltage supplied to the CRT, the image produced on the phosphorescent screen will initially appear as a series of point-like spots, and over time these spots will fill in the area corresponding to the shape of the hole drilled in the anode. This seems to suggest that things move from the cathode to the anode, and some move further through the hole drilled in the anode to the phosphorescent screen. Those things seem to be point-like in nature, i.e. particles, which in the case of the electromagnetic dipole just described are called electrons. If we create an opening in the shape of a long rectangle in the anode of a CRT apparatus, the image formed on the phosphor-coated screen will be in that same shape. However, as we narrow the width of the rectangular opening past a certain point, the image appearing on the phosphorescent screen actually begins to widen. This widening of the image occurs whether the voltage is high and a constant stream of energy is being transmitted to the screen, or whether the voltage is low and individual spots on the screen are lit in slow succession. The widening of the image on the screen mirrors the wave phenomenon of refraction. If waves in water run up against a barrier with a gap that is large relative to their wavelength, the waves will move through that gap in basically the same direction they had previously moved. If that gap is narrow relative to their wavelength, the waves will be refracted upon passing through the barrier. The waves will be scattered into a wider arc. The widening of the image appearing on the phosphor-coated screen in a single-slit CRT apparatus seems to suggest that the electron beam is refracted and therefore possesses wave-like properties. So in the case of extremely low voltage, where single units of charge create single spots on the screen at long intervals of time, how does refraction, a spatially distributed phenomenon, occur in tandem with the point-like, spatially discrete spots on the screen? If we create a second parallel slit in the anode of a CRT device, the image appearing on the screen will take the form of a series of parallel lines. This series of lines corresponds to the interference pattern that would be formed if water passed through a barrier with 2 gaps. Where the 2 waves overlap at a crest, the crest is amplified. Where they overlap at a trough, the trough is brought lower. If we measured the amplitude of the 2 interacting waves along a line perpendicular to their direction of travel and parallel to the barrier, we would see the same sort of interference pattern that occurs on the phosphorescent screen in the double-slit experiment. There are spots on the phosphorescent screen which are lit in the single-slit refraction pattern, but which are not lit in the double-slit interference pattern, those spots where the troughs of the 2 waves intersect. In other words, an electron can access some points on the screen when one slit is open, but when that same slit remains open and an additional slit is now introduced, the electron can no longer access those same points on the screen. In a low voltage version of the double slit experiment, where a single spot is detected only intermittently. A single electron seems to be able to interfere with itself in transit, as if it spreads itself out, passes through both slits as a wave, and then collapses back into a point on interacting with the screen. If, attempting to discover what does happen with the electron, we place a detector between the two slits in the anode that allows us to recover information about the path of each electron, the interference pattern is lost, and the image appearing on the screen will be two parallel rectangles. An idealized detector might be a proton suspended in a cavity between the two slits. When an electron passes to the left, the proton will be attracted to the left and will impact the wall of its cavity on that side. The experimenter could then open up that cavity and see which way the proton had gone to infer the path of the electron. It seems that when there's no way to gain information about the position or momentum of a particle, the particle spreads itself out and takes all those paths which it might possibly take. But when we can gain information about its position or momentum, it narrows its spread to conform to the measurements we are afforded. In classical physics, the direction of a magnetic system's north and south poles is influenced by its angular momentum, or the way it is spinning. Angular momentum in classical physics can take a spectrum of possible values. A ball spinning on its axis can have its axis oriented in whatever way. In quantum mechanical phenomena, something analogous to angular momentum does seem to apply to individual particles and atoms, but the possible values of their spin are not continuous, but discrete, in some cases including electrons taking up only one of two possible values. We can see how this appears to be the case using a Stern-Gerlach apparatus. A Stern-Gerlach apparatus creates an asymmetric magnetic field, the north pole of the magnet being stronger than the south pole. If we aim an electron gun, like a CRT, between the north and south poles, and the nature of the electron spin is such that its north pole is oriented towards the north pole of the Stern-Gerlach, then the electron will be repelled away from that stronger north pole, and it will follow a trajectory tilted towards the south pole of the Stern-Gerlach. If the electron spin is such that its south pole is oriented towards the north pole of the Stern-Gerlach, then the electron will be attracted toward the north pole of the Stern-Gerlach, and its trajectory will be shifted in that direction. If we place a phosphor-coated screen behind the Stern-Gerlach, we can see which way the electrons are deflected, and thus what the value of their spin is. If the electron's angular momentum could take up a continuous spectrum of values, if it could spin whichever way, then the image on the phosphorescent screen would be a continuously filled-in eye-shaped distribution pattern. Particles would be more deflected either way, which passed directly through the center of the Stern-Gerlach, and would be less deflected either way, which passed somewhat to the right or left of its north-south axis. We don't see a continuous eye-shaped distribution pattern, however. We see the outline of an eye-shaped distribution pattern. Each electron takes a binary value of either spin up or spin down. The electron won't specify any more information about the orientation of its north-south axis than that. Either its angular momentum only has two possible values, or the electron is being vague in telling us about itself. If we remove the phosphorescent screen and place Stern-Gerlach devices along the upper and lower paths of deflection, the upper and lower lids of the eye, then all of the electrons taking the upspin, upper deflection path, will once again be deflected up by the new Stern-Gerlach apparatus along that upper path. And all electrons taking the downspin, downward path, will be deflected down by the new Stern-Gerlach device situated along the lower path. If we place phosphorescent screens behind the upper and lower Stern-Gerlach devices, we'll see the image only of the upper lid of the eye behind the upper device, and that of the lower lid of the eye behind the lower device. The information we gained about the electron's paths of deflection, and by inference their spin, has so far only been with regard to one particular and arbitrary orientation of the north-south axis of the original Stern-Gerlach device. We can rotate the device in whatever direction and yield a fresh eye-shaped deflection distribution oriented corresponding to that rotation. Let's call the north-south axis we started with the y-axis, and the electrons that took the upper deflection path y-spin up electrons. Using Stern-Gerlach devices, we can intentionally prepare an electron beam that will be constituted entirely of y-spin up or y-spin down electrons. So what happens if we pass a beam of y-spin up electrons through a Stern-Gerlach device oriented at a right angle to the original one, i.e. a Stern-Gerlach device with its north-south pole oriented along the x-axis? Once again, we will see a binary distribution pattern, now turned on its side, dividing the beam into x-spin up electrons and x-spin down electrons. Have we now just increased the amount of information we have about the electrons? Do we have a beam of electrons that is x-spin up and y-spin down, or x-spin down, y-spin up, or x up, or x down, y down? No. If we pass the x-spin up electrons, which we had previously measured to be y-spin up, once again through a y-oriented Stern-Gerlach device, we'll get a fresh I-shaped distribution pattern going both up and down. So once we measure x-spin, the particles forget about any y-spin they might have had. Maybe there's something physically happening when the electron passes through the Stern-Gerlach that forces it into one of two spin values and wipes out any previous spin it might have had. Our next experiment demonstrates that this cannot be the case. If we take a prepared stream of x-spin up electrons and pass them through a y-oriented Stern-Gerlach, the beam will divide into two, one with y-spin up electrons, the other with y-spin down electrons. If we then place reflectors along the paths of both y-up and y-down beams, oriented to cause the two beams to once again converge into a recombiner, which aims the recombined beams together into an x-oriented Stern-Gerlach device, that device will only deflect the beam in the x-spin up direction. So the original x-spin value of the original beam has somehow been retained despite the fact that it had been physically separated by a y-oriented Stern-Gerlach apparatus into y-spin up and y-spin down values. If the Stern-Gerlach physically scrambled the information about other axes of spin, then the original x-spin up would have been lost in the interferometer. It seems that an electron is satisfied sticking to the minimal spin information it gives us, even if it's physically gone through other spin orientations, provided we can't access the information to specify which values the electron took along those other orientations. As long as we can know about its y-spin value, it won't tell us its x-spin value, and vice versa. If two electrons be prepared such that they share the same quantum state, share the same distribution of probable measurement outcomes, we can't specify any information that distinguishes one from the other. We can, however, divide the entangled system widely in space, provided no interactions impinge upon the system which would allow us to recover information about one or the other particle which would differentiate the two. If we send such a system on two divergent paths, say a mile apart, and then measure one end of the system with a Stern-Gerlach apparatus and find that the electron at that measurement location is x-spin up, then we can predict with certainty that the other formally entangled electron will be measured as x-spin down. The idea that each half of the entangled pair always has its respective x-spin value, but does not disclose it until measurement, the idea that such systems have local hidden variables, was ruled out by experimental confirmation of Bell's inequalities. For more complex entangled systems, John Bell proved mathematically that there was no combination of already existing local values the particles might have that could account for the specification of those variables which occurs at measurement. Experimental confirmation came decades later. When measurement of one element of an entangled system occurs, immediately the complementary values for the other elements of that system are set. This is the spooky action at a distance that Einstein was concerned about in the famous EPR paper. The basic questions to be answered in interpreting these phenomena are: What actually are elementary particles? Are they point-like objects? Are they distributed in waves? Why are they so shy about giving too much information about themselves? When we specify one value which characterizes them, why do we simultaneously lose information we might have had about other values which characterize them? I.e., why does Heisenberg's uncertainty principle hold? Why does measurement of entangled systems have non-local effects? What constitutes a measurement in the first place? As I said previously, the worldview of perennialism has a ready interpretation for these phenomena. I'll describe the ontology and dynamics of perennialism, and then show how these account for the experimental results of quantum mechanics. Reality as a whole is not complex, but simple. The appearance of complexity and separation stems from our adoption of various perspectives on reality. A perspective is characterized by the presence of certain experiences and the absence of other experiences. It is also characterized by a particular locus for its frame of reference. The characterization of specific properties, in all cases, is dependent upon the adoption of a perspective. Spatial or temporal extent is never absolute. It always depends on a reference frame. If you could take a view from nowhere on reality as a whole without adopting a perspective, there would be no left or right, forward or back, small or large. There would be no distinctions along any dimensional axis, because all dimensional distinctions are dependent on a particular origin point for the reference frame which characterizes them. Taking no perspective at all would yield an absolute simplicity. Likewise, taking all perspectives at once and having an origin point for one's reference frame that is globally distributed would yield an absolute simplicity, because all points would be equally distant from the origin along every possible dimensional axis. If reality as a whole was, ontologically speaking, a discrete set of fundamentally separate things, rather than a unity as a whole, then how could those separate things relate to each other? For two things to relate, they must have something in common. For them to occupy two distinct positions relative to each other, they must, at least, both have the property of possessing position. Two things cannot be absolutely distinct and mutually exist. Distinctions are always relative to some common syntax of possible relations, some common law regarding how distinctions work in the first place, and that underlying syntax of possible relations, if it has distinct components, must itself be held together by a yet deeper underlying syntax determining the possibility of those higher order syntactic relations. Taking this process to its conclusion, known as syndiphionic regression in the CTMU, we reach a universal aspect of all beings that implicitly contains the possibility of all more complex relations. That universal aspect is simple and the principle of all higher order. Reality viewed from a perspective is complex. Reality taken as a whole is not complex. Reality taken from a perspective has certain ontological limits. Reality as a whole does not have those limits. The observable universe for us has limits, but the scope of possible observation for all possible observers is infinite, being limited only by the syntactic laws that render them coherent as observations in the first place. The determination of all observed variables, position, velocity, mass, momentum, spin, etc., is coeval with observation itself. That is, they are determined with the perspective we take, and not independently of it. Temporal relations are determined from a particular perspective. The past hasn't ceased to be ontologically. The future isn't yet to be ontologically. They are only behind us or before us as possible transformations of configuration of the state of our present perspective. All possible perspectives on reality exist simultaneously as a one ontologically. Perspectives are neither created nor destroyed. Material causation doesn't create a new state of affairs. It tracks consistent lines of transformation from one perspective to another. One perspective doesn't have an absolute relation to all other perspectives. It only has the relations that are specified in its own identity. Beyond those specifications, its context is indeterminate. All distinctions are a product of perspective, so the distinction of which future state will succeed your present perspective is simply not made. Each perspective exists with respect to a superposition of possible futures and of possible spatial contexts. The position of each particle is not absolutely determined. The position of particles is restricted to a range of values that could, in principle, be contemporarily related to actually observed variables. There are the point-like exact specifications made explicit in a perspective, and there are the probabilistically distributed, implicit, possible values that the energy associated with those point-like specifications can take on and maintain spatiotemporal continuity. The superposition of possible temporal and spatial contexts that an observer might find themselves in is restricted to the values for all observables which are consistent with the conservation of energy. Conservation of energy, as Kant observed, is that which allows temporal transformations to exist as meaningful structures. It is the sameness underlying the difference that differentiates a valid temporal sequence of perspectives from a random collection of unrelated moments. We know this principle as the conservation of energy, but as we now know in modern physics, energy is not only the same thing fundamentally as mass, but also the same thing as information. Conservation of information is what allows for a meaningful sequence of experiences. That's why electrons are shy about giving out too much information. Information can't be created or destroyed. Ontologically speaking, the essence of the objects of our observation is characterized best by the term information, as understood in Shannon's original sense. Information specifies distinctions. A unit of information, a unit of energy or mass therefore, is not an absolute value unto itself, but rather a measurement, a specification of a set of possible differential relations. Perceptual reality doesn't boil down to a set of discrete objects, but a set of distinctions, a set of relations between relata, which are not independent things, but which are inseparable from their mutual status as relata. This is essentially what mathematics is as well. Abstract objects whose identities are defined by their relations to other abstract objects. The most primitive kind of mathematical object is a binary distinction, an indication of presence or absence, 1 or 0. Likewise, the most basic kind of data accessible to us in perceptual reality is an indication of presence or absence. All higher-order mathematical relations can be rewritten as a long set of binary relations. All higher-order perceptual objects can be decomposed into a long set of bare ontological indications, the presence or absence of the quantum of a system. The set of all possible perspectives is the same as the set of all possible mathematical relations. The simplest possible mathematical relations are built from the number 1. The 1, prior to perspective, is fundamental. The first images, or emanations of the 1, are the simplest forms, i.e. the simplest possible perspectives. Every more complex perspective, i.e. form, i.e. mathematical relation, depends for its existence on the more simple perspectives. The bit of information must precede all more complex informational encodings. That's why systems exhibit quantum properties at all. The simplest systems, the smallest systems, are closest to simplicity, and mathematically speaking, the closest forms to simplicity are the natural numbers. If the smallest systems could be measured along the infinite continuum of possible values, then they would specify an infinite amount of information. Perspectives are not infinite, they are finite. Simple systems display wave-like properties because there is, ontologically speaking, a range of values that a unit of energy, that is, information, might take and remain spatiotemporally consistent with our other observations. So now we're ready to look again at those basic experiments. In the cathode ray tube, the amount of energy going into the system is known to the experimenter, or is in principle knowable. The particular trajectory of each electron along the wave function of its temporally consistent values is not determined by observation until the perspective of the experimenter takes view of the phosphor-coated screen. Point-like splotches occur on the screen because a finite amount of energy can only be transferred to a finite number of phosphor molecules. A moment before the electron hits the screen, it is a distributed wave of energetic potential. There are many possible paths the electron could be taking that are consistent with its ultimate outcome. The perspective of the instant of interaction with the screen determines the specific position of the interaction by its own identity. The wave function of the electron's possible former values is drawn backward in time. No collapse occurs ontologically. Wave function of possible states are always drawn backward and forward from the specified observations within a perspective. Refraction occurs because the narrowing of the slit specifies the possible position of electrons just past the anode. Because energy equals information, the information we gain through the specification of position to preserve conservation of energy must be accompanied by a loss of information about momentum. The distribution of possible values for momentum becomes wider, and therefore the image appearing on the screen is stretched. The probability distribution of possible values for currently unobserved particles whose energetic potential is already part of the total energy of the perspective system behaves like a wave does in that it spreads out in space over time because temporal distance from the last observational tracking of that unit of energy yields a broader range of temporally consistent values for its spatial position. The interference pattern is produced from the same principle. The range of spatiotemporally consistent positions of the unit of energy traveling through the system spreads out over the course of its trajectory like a wave does. And the amplitude of the probability wave, corresponding to the crests and troughs of a wave in water, oscillates because there is a finite range of amplitude values that are each consistent with the conservation of energy. It might be indifferent to us, prior to observation, whether the amplitude of the wave function at a point is 1, 0, or -1, and so these values are probabilistically distributed over the wave function. When we add the detector to the double-slit experiment, we destroy the interference pattern because if the detector stores information for us about the path of the electron, we retroactively render that element of the probability wave null, which is inconsistent with the temporally accessible perspective which examines the detector. The information we can have about the spin of an electron is detectably quantized because the electron has a very small amount of mass/energy, and therefore a very small amount of information that it can specify. If the electron could specify for us whether it was oriented in one of an infinite and continuously distributed number of ways, then it would be providing an infinite amount of information, which would mean it had an infinite amount of energy/mass. The determination of the distinction of its spin value occurs when we ask the question about its spin. It is coeval with our perspective. If we could combine multiple Stern-Gerlach devices to specify more and more information about the electrons, then their energy would be increasing, which would violate the conservation of energy. The x-spin up information is recoverable at the end because that information was present at the beginning. Information equals mass equals energy. So if that information was lost without a compensating gain of information of y-spin, then that information would have been destroyed. Conservation of information is what defines a coherent timeline in the first place. The perspectives identical to that of the experimenter upon measuring the final x-spin value, except which measure 50-50 x up and x down, are perspectives with therefore different total energy values, and therefore are not members of the same timelines. It should be easy now to see why entangled systems collapse and determine their values non-locally. The entangled electron pair, the singlet, due to the nature of its preparation, is known to be composed of one upspin and one downspin electron on a given axis of measurement. If we determine a perspective which includes an observation of upspin at one location, we immediately eliminate from spatiotemporal continuity any perspective which observes anything but downspin for the other member of that formerly entangled pair. Otherwise, there would be a loss of total information, and a violation of conservation of energy. According to perennialism, the differentiated world is projected by the universal aspect of the soul, the underlying syntactic core that I previously identified. Objects don't exist ontologically separate in a material world whether or not anyone looks at them. They are determined only through Purusha's projection, or the adoption of a perspective. Time is an illusion. Causal processes don't create anything. They can only track the web of constraints placed upon the observer by its attachment to the object of its own projection. Timelines are anthropically selected, in other words, and are not ontologically primitive. The nature of the creation of a perspective always involves a trade-off, an attraction to some experience and an aversion to another, the centrality of one locus and the peripheralization of another, yin and yang, love and strife, etc. The various objects of experience aren't things by themselves. They are only relata in the relations drawn by the trade-off inherent in our attachment to the world illusion. The negative charge only exists because the positive charge exists. As far as the properties of the perceptual world go, they are always aspects of relationships, never things in isolation from us and from each other. The most primitive aspects of such relationships reduce to the laws of number and harmony, as Pythagoras observed. Perceptual reality is quantized because its existence is dependent on the symmetry of basic mathematical relations. All more complex forms descend from the one, and the one can be found in them. There are other aspects of the intersection of perennialism and modern physics that I haven't gone into here. If you found this video interesting, please consider supporting the channel so I can put more time into exploring and explaining this subject. The link to my Patreon is in the description. As always, I invite you to share your thoughts in the comment section. I try to do my best to address everyone's questions and criticisms. And if you'd like to get involved in related research or just chat with others in these circles, the link to the Peer Academy Discord is also in the description. Thank you for listening.